Okay, so I gave back the homework too, as well as the midterm. So something about the midterm I want to talk about. No. Okay, so based on 14 students who have done both parts, and I graded those, the mean is out of 50, the mean is 39.3, and the median is 41.5, sorry. Yeah, so that's based on 14 students who have completed both the return and the take home. Okay, I will send an email about this as well. And as usual, we're gonna do corrections, and the correction work in this way, so the total is 50, and then you can come sign up for an appointment and then talk to me in person is how you're gonna redo the questions, both the take home and the written part. You can do both. And I would appreciate if you bring like some kind of write-up before you come, because obviously there are a lot of stuff going on. And especially with the take home, I think it's easier if you do it again already and then just show me what you have done wrong or what you think you would have done correctly. And then for this time, we're gonna do a 50% back correction. So if you say, if you got 40 out of 50, and then for the missed 10 points, if you got all of them right, and then you're gonna get 5 points back, something like that. Okay? Yeah, so I will send an email about all of this. I mean, obviously not everybody's in class today, so all of the information needs to be conveyed as well. So that's so much about the midterm. And then, of course, if you have like any regrade issues here and there, as well as not only the midterm, but homework, feel free to talk to me. I guess we'll have, so tomorrow I will have some hours available. So if you want to, because I understand Friday is the drop and NRO deadline. So if you want to talk about any of this, I mean, feel free to come in tomorrow. I will have some hours for corrections or just office hours, et cetera, et cetera. So email me if you want to do that. And overall, I think the majority of students are doing well. And yeah, so if you don't feel like you're doing too well, please come to talk to me, and then we can talk about in particular in what aspects that you think you're missing in terms of how you can improve. Again, because we're doing a 50% correction, so you can also gauge, say, even if by the end of this week, you won't be able to come in to do corrections, but you can still imagine that, okay, if you can get all of them right, even after the break, you can have a feeling of how much how well you're doing. So yeah, so that will be the midterm part. Again, if you're gonna do corrections, don't talk to your friends or like fellow classmates about the questions. I would really appreciate that, because again, if you sign up for a correction appointment, that means you're gonna independently, you can spend as much as you want time, but you don't talk to others about how you're gonna solve them. Okay, just to be fair for everyone. Okay, and okay, so I think then we'll be able to start today's lecture. And today we actually will just try to finish the normal, because as if you have tried deriving it, you will notice that it's pretty complicated to do that particular derivation. And I mean, for the 2-parameter model case. So we're gonna do most of it today, but I won't tell like exactly step by step how you're gonna do it, because I want to assign that as a homework question. So for everyone can make sure that you know how to do it. But for today, we're gonna go over part of it, the key parts, and then as well as some, in particular, I think in class, it makes more sense to do, look at some examples and how things are done in practice, okay? All right, so, okay, so for the normal mean and variance, in this case, we're doing a 2-parameter model. That means you assume that both the mean and variance are unknown, and then you're trying to put prior on it. And then obviously it's gonna be 2 priors, one for the mean, one for the variance. And we're gonna look at how you can do it. So there is a standard way, as you can see, that people have worked out it before, that if you put a certain prior, two priors, certain 2 priors over there, you're gonna get some nice results. So this is the one that we're gonna work with mostly for this particular chapter. And again, all of these results are very relevant later, because again, the normal model is so commonly used that even later, if you're looking at like say hierarchical modeling, et cetera, you will still see the normal model here and there. So it's very important, I think, for us to understand at this moment how the derivations are done and how, in particular, to interpret what the mean and variance in the posterior mean to us. Okay, because as you can see before, for the one parameter model case back here, we have seen that the mean, posterior mean, is weighted average. So like some weight y1, w1 with mu 0 plus some weight of y bar, and then both of the weights are related to the position, right? So that's what we have seen before. And even for the position, post position, it's gonna be the prior position plus the data position. So this is what we have seen before, and realize that when we're talking about the posterior back then, we're talking about the posterior on the mean, because that's the only parameter that we're making inference about. Okay? But even so, back then, we realized that, okay, you will be able to identify what is the mean and what is the position in the posterior, and what do they mean? How do you combine information from the prior and the data? And but now we're going to move to the third point where you have two parameter models. So obviously, before we actually start doing all of this, I just want to give a heads up, because there are going to be so many terms related, like in this case. So you're going to have the theta, which is the mean, and then sigma square. Okay, and you notice that we're going to work exclusively with phi, which is the precision, because it's kind of easier to work with, and the results look more, I think, nicer at least. So we're going to have a prior 1 is on theta, and prior 2 is on this phi. Okay, so you will see that, and in particular, you will see that the first prior is actually given. It's a conditional prior in some sense, theta given phi. Okay, so I want you to keep in mind that right now we're talking about two priors. Okay, and then in each of the prior, we're going to start talking about like prior sample size. We're going to start talking about this and that, and then so be sure that we're really talking about two things and don't get confused. Okay, but again, you see that in the prior, theta is given phi, and then later when you are doing the posterior derivation, you see that, okay, we're gonna get two posterior as well. The first one is theta given phi, and y1 to yn, okay? And then a second posterior, which is on the precision, it's gonna be phi given y1 to yn. Okay, so just a heads up, like this is how things are. So this is how the setup is, and you will see that. So let me just show you something before we start looking at the example. Let me use phi over here. Okay, so you see that the prior is theta given phi. Here, this prior is phi itself. So it's a conditional and a marginal. Okay, in the posterior as well, you have conditional, and this one is not marginal, of course, because it's conditioning on the data, but it's still marginal in terms of phi. Okay, so I want to show you that the way that we're doing all of this is we actually start with a joint prior that you come up with theta and phi, which is the product of the conditional times the marginal. Okay, so this is the basic assumption that we start with once you start to have multiple parameters. Because in the one parameter case in the past, you don't have to worry about any of this. You only have one parameter, so you just do, say, theta, and then theta given y. Okay, but now you have two parameters, and later you have more parameters. The goal, like the general procedure, is actually the same. You start with a joint prior, and you're gonna arrive at a joint posterior. Okay, so in terms of probability, you will see that this is what we're trying to get. right? You start with a joint prior, theta and phi, and you end at a joint posterior, theta and phi, given all of the data. Okay, so sometimes it makes sense to have like independent priors like phi, marginal phi, marginal theta, etc., etc. But for the normal case, oh, sorry, go ahead. Oh, okay, yeah. So then for the normal case, for this normal model, for the two parameter, we're doing a margin of the precision and then a conditional of the mean given the precision. So it works in the prior in the same sense. And then once you move to the posterior, it's the same. Like it's phi given y in terms of marginal, and then in terms of the conditional, it's going to be theta given phi. Okay, so notice that here in the second posterior, in the condition, there's no phi over here. Oh, sorry, there's no theta over there because that's not how things are set up. Okay, but once you multiply these two together, you get the joint, and that's what we start with. And then once you multiply these two things together, it's going to get the joint posterior. Yes, Katie. Oh, switching? Yeah, good point. So why don't you switch? I guess it's just super hard to do the switch way. Yeah, I mean, you can, so this is a really good question. So once we have multiple parameters, how are you going to do things, right? So for the normal model, all I know, or most what the textbooks or like what the methodology have been developing, is always this way. And I think it's just easier to do this in this way, because say soon you're going to see that this is a normal, right? And this is a gamma. Right? And then this arrives to be a normal, and this arrives to be a gamma. Okay? I guess in theory, you can do the other way. And you might want to go back to try it if you want. It might be very complicated to do. And I think there's a reason why in the end, people usually do this. And I think for the normal model case, it's just this setup works. Yeah. And I guess for other cases, you might want to try. So, but this really brings a really key question here. Once you have multiple multiple parameters, what you're going to do. Okay, so one way for the normal model that we're learning here is in order to get the joint, you get a marginal and a conditional, and you multiply them together. And then for the normal case, somehow if you put a normal for the conditional and for a gamma for the marginal, it works out that the marginal again in the posterior going to be its gamma, and then the conditional in the posterior going to be normal again. Okay, but even, yeah, like right now I just want to like bring the big picture, and you will see that later on when we move to other models, it's working in a similar way. Okay, so once you have multiple parameter, what you're going to do, you start with the joint prior and you try to arrive at the joint posterior, but you have to work it out, the detail as how you're going to set it up, and set it up in the way that it works for the modeling itself. Okay. Mm-hmm. Anything else? Earlier I emailed you, asked you to try the derivation, just because you see that here you have two parameters and then you have a bunch of data, and then it's still straightforward task over here that you get theta given phi, and then phi over here, and in the posterior you are given exactly what you're doing if you follow the handout that I provided. And also, I mean, just one of the midterm exam questions, you notice that in a brand new situation, you might be asked to do that as well. And then you really need to do it step by step. Just sit down, don't worry too much, look at the terms clearly, okay? And I think based on like the questions during the exam as well as the grading, I just realized I think people's probability basics are not everybody is pretty fluent with that. And I think that will be something that we should all focus on. And that's why I asked you to try to derive it. And you see that like in exams or in real applications, you might try to come up with something new, and then over there, it's the same procedure, but you need to make sure that you know how things are done, okay? And then how the probability, how all of the calculus, how the integration is working, and it's all actually from a course like 241. So I tried to do the review, but I guess we still need to do a little bit more. So let's all try to focus that as well. All right, so there's this, and let's start this lecture by looking at a motivating example as why we want to do this, and then get into the derivation a little bit, okay? Okay. So there's this Pygmalion study trying to evaluate whether teachers' expectations gonna impact the academic development of children. Okay, so for all of those experiments, they try to come up with two groups. I guess you have heard about those terms before. You try to do an experiment, you will try to have a control group and then a study group, or like an experiment group. So here, the researchers gave IQ tests for elementary school children. And they actually, so this second bullet point over here is trying to do how to put people randomly into two groups, because you want to have one to control. So you can actually really attribute the results in the end to the fact that they're in different groups. So they randomly picked 6 children and told the teachers that the test predicts them to have very high potential for accelerated growth. And they also picked another 6 children and told teacher that the test predicts them to have no potential for growth. And at the end of the year, they gave the IQ test again to all of the 12 students, and then they're gonna record the change in the IQ test, in the IQ scores of each student. So this is set up. You have 12 kids, 6 in one, 6 in another, and one in the first group, they're told that they're really smart and they're doing really well and they can do even better. And then the other one is not being told that, and actually like just say that no potential for growth. So now the interest, because now you recorded the change of the IQ scores. And I guess it makes sense to think about, okay, now I have group A and group B. If I have 6 in group A, 6 in group B, I want to test if the change, say, in the first group is really, say, significantly larger than the other group, right? This will be a natural question people would like to ask, because now you have 2 groups, and then you want to see how the effect of what the teacher being told gonna affect the academic development of children, okay? And then here, they're trying to use the measure of IQ score change as a measure of the academic development. Okay, all right, so let me just tell you a little bit about the data. So for the accelerated group, we labeled it as A. We had 6 changes, okay, because now we're looking at the change in IQ score. And in the no growth group N, you also have 6 changes, okay? So I can tell you some summary statistics here. I can give you the mean of each group, which is for the A group is 15.2, for the N group is 6.2, and I'll also give you the standard deviation for both, okay? Yeah. So before we move on to the Bayesian methods, I want to just talk a little bit about what do you think, or what, without the Bayesian methods, what people can do, or what people usually do. So first of all, it's super small sample size, okay? You only have 6 observations in each. And then even so, even if you don't have, even if you have a large sample size, in order to derive, if you don't actually know about all of the normal theory for the frequentist method, you'll have to derive it, and it's very complicated as well. But mostly, I think it's because the observation is small, then using any kind of frequentist method is not that well justified, okay? Because any of the, so if you're trying to do the difference of 2 means, you know that it's going to be a normal distribution, and then it's going to have a specific variance and specific mean, and all of those are based on the large sample assumption. If you're trying to just do the t-test that you probably have heard before. Okay, so the drawback over there is that you need to have large sample size, so this is not working for that. All right, so something that we can think about doing. So first of all, IQ test scores are well known to be approximately normally distributed. I don't know if you have heard this before. And so suppose that is true, and that's the basic assumption that we're gonna do, then you can have 2 normal distribution, and then we want to get the mean, the difference of the mean of these 2, okay? So pay attention that this is true no matter what you're doing frequentist or Bayesian methods. These are the data, okay, samples. And this is the true mean of the population. This is the true variance of the population. okay? So the interest that people are trying to make inference about is on the population parameter, okay? Because you have one sample, 6 children, you have another sample, another 6 children, and all of them, so each of the 2 groups coming from 2 populations that you're trying to evaluate, okay? And then for any kind of hypothesis testing, not only in the frequentist methods, but also in the Bayesian paradigm, you're trying to make inference about, say in this case, it's really about mu A minus mu N, okay? It's about the true mean of the accelerated group and the true mean of the no growth group, and then try to see if there is a difference over there, okay? All right, so in order to make inference in the frequentist paradigm, if the 2 variants are not the same, it can be very complicated, but I want to show you that it is trivial with Bayesian inference, but of course you have to go all the way to make sure that you know how to derive it. But once you get there, a lot of the analysis becomes very straightforward, okay? So maybe just a really a quick go back a little bit. So in the 1 parameter case, remember, like in the textbook, when we're looking at the image length, the wing length example, like you don't even need R to do it. Remember? Like, because you kind of already derive all of the posterior that it should follow, right? So you know exactly what the form is going to be, unless you want to do multi-color approximations, say predicted distributions. Otherwise, you know exactly what the posterior normal will be, right? And then you can summarize everything from that normal distribution already. So this is true, again, for the 2 parameter case, okay? You will see that you'll be able to derive the exact posterior for the phi, which is precision, and also the exact posterior for theta given phi, which is the mean, okay? And then once you have done that, you'll realize that you don't even need R to do any of those for you, because you have the exact analytic solution in the end. Okay, so I would say this is one of the features I think appealing about the Bayesian normal model in this particular context, because you actually can derive it directly into the analytic solution. And some people feel more comfortable if you have that, which is, I think, understandable. But then, of course, if you try to do predictions, you need the power of simulations later on. Okay, all right, so, okay, so I should say, it is trivial once you have done all of the derivation. And once we go over this lecture, we're just gonna take those as granted, okay? But we still need to see how you can arrive there, because it's not something super crazy that I cannot do. It's just a little bit tedious, and there are some tricks here and there that we should brush up. All right. So let me just introduce the normal model a little bit, and then I actually printed out again the handouts that I shared, because I told you I mistyped some of the meanings here and there. So if you take a look at it, right, and if not, you can use this as a handout, and we'll talk about it. Right, yeah, so it's on Moodle as well, and it's under this chapter. Okay. So I talked about, so the front page, we actually started it last Wednesday. And then, but for us today, we're gonna focus on the second part, the second page of this document. So the front page is really just building up what I said before. Okay, you start with the joint prior, and then you try to derive it, like try to arrive at certain results. And on the front page, I just wrote down what the textbook was writing. Okay, I told you what the results are, and in particular, you notice that they're using sigma square everywhere. Okay, they're using the variance directly, even though they're using 1 over sigma square to represent the precision, but in the notation, they use sigma square here and there. And that's what the textbook uses, which is fine. But personally, as well as the way that I got trained, I preferred using the precision. So I showed everything on the second page for you. So let's all turn to the second page. So yeah, we can go to the slides in a minute, but we can look at, if you can look at the second page, I just want to describe the situation a little bit and then let you to break into smaller teams to make sure you can exchange what you have done before, and then we can come back as a bigger class. So instead of the 1 over sigma square, we're gonna work with precision notation. We use phi, so it's 1 over sigma square. So the joint of theta, which is the mean, and sigma squared, the variance, becomes the joint of the mean theta and the precision phi. Okay, nothing complicated here. And then in particular, we're gonna use this notation. Let's have phi follow a gamma distribution. So we used gamma A, B before, but now bear with me, use this nu 0 over 2, and again, we want to make it interpretable, so we won't do it.
The thing I didn't understand is SS not a single quantity, or is it the multiplication of a quantity S times quantity S naught?
Oh, sorry, it's just one notation.
Okay.
Sorry, yeah, you can think of it as scalar. Yeah, sorry about that. Yeah, so it's SS null. Yeah, so pretty much it's very similar to the SS that we'll define in a minute.
Okay.
Yeah, and then that's trying to show you the information that is carried in the prior. Okay, it's one thing. Okay. All right, so you're gonna have a gamma prior for phi, and then I wrote the kernel for you. Now notice that I'm using proportional sign here and there. So I know it's gamma nu 0 over 2 and SS null over 2. So I know in the kernel, because it's gamma, what the marginal phi will be in the prior. And then I also give you the normal prior of theta given phi, and center of mu 0, and also the variance is 1 over kappa 0 phi. So this is very similar to what we have seen before. Okay, it's sigma square over kappa 0. Remember in the one parameter case, but now I replace sigma squared with 1 over phi. Okay, so that's what it is. And then I wrote the kernel for you as well. And then I wrote down some lines of the normal likelihood, which you might be wondering how you can get there. So that's one of the exercises I want you to try, and then we're going to talk about it. So you see that the joint likelihood, y1 to yn, given the mean and variance, can be simplified into the third line that I wrote over there. Okay, so there are some tricks here and there, which we're going to go over, and that's very important for any kind of normal, any kind of derivation with normal model. And then also, like earlier, Eli was asking what is SS null. So it's really like an equivalent. You can think of it as what for the prior as SS for the data. So if you look at the third bullet point of the normal likelihood part, I wrote the sample sum of squares, which is capital SS. That's S squared times n minus 1, which if you look at it will be the sum. It's pretty much just the sample sum of squares. Okay, you sum all of the yi minus y bar and then take the square. Okay, so S squared is the sample variance, right? So the sample variance is derived by sum of all of the square term divided by n minus 1, right? So I pretty much just bring it back. Instead of thinking about the mean sum of squares, I'm looking at just the total sum of squares, which is going to be capital SS. Okay, so you can think of this as deviations, right? It's variance related to variance. So it's deviation of each observation from its sample mean. Okay, take the square and then sum them up. So we use SS over there, trying to carry the information from the data, how variable, say, the data is from its mean. And then comes the last part. I show you the results directly over there, but of course, arriving there, it's going to take some work. But in the end, you will see that under this normal gamma prior distribution, the posterior distributions is another normal and another gamma. Okay, so phi given the data will be a gamma, and then theta given phi and the data are going to be a normal. And then yes, there's obviously some work needs to be done in all of the steps. So I want you to, for now, focus on the first part, which is how to simplify the normal likelihood that I show you in that 3 lines. But there are some missing steps here and there that I want you to, I hope you have done it a little bit before the class. And let's spend like 2, 3, 4, 5 minutes to see how you're doing it. And then you can talk to whoever is close to next to you, and then you can make sure that we all know how to do it. So just really quick, the first line is just directly from the likelihood. And then the first trick that you would notice that you need to do is just one step, and then you can go back. It's rewrite yi minus theta to be yi minus y bar minus parenthesis theta minus y bar. Okay, I mean, I guess you might try to guess like how you come up with that, especially from like the second line. You will see that you break the exponent into two parts. Okay, and this is the first trick that you will have to do. And again, maybe that first time you won't see like the point of why we're doing this, but later on you will see that this is a pretty standard practice, and then that makes the interpretation of the results much simpler. Okay, so good. So go from here, try to arrive at the likelihood as much as you can. I think this is a key part that many of you might not know. Oh, it's probably not in that order. So, yeah, it's not the same. Yeah, it's strange. Yeah, it's strange. So you see that like there are multiple, I think, two reasonings of why we want to break the sum of yi minus theta squared into these two parts. Okay? The first reason that I can come up with is you're trying to break it up into two parts. The first part is about the data itself, right? Because it's about the yi and the y bar, and that's everything you can get from the data. You try to separate that from the rest. And the rest over here is about the mean that you believe the normal model should have, and then y bar. Okay? And another reason is you can see that once you break that in this way, the whole term down here, once you do the algebra, you realize is 0. Okay? So the key steps I wrote over here. So first of all, based on some comments. First of all, this summation is applied on the entire term. Let me use a different color. Yeah, so this summation is applied on the entire term, okay? So, and also summation is applied on the yi, okay? It's I from 1 to n. So this term still has yi, so you keep it. This term, there's no yi at all, and it's just like n copies of it. So that's why this is that n over here, okay? And the last one is summation. I keep this summation sign over here. And then here, I'm just like complete the terms over here. And then, so by the way, from this step to this step, not like every term is not in the same order that it's supposed to be. Sorry, I just wrote it up. I just wanted to cancel this and cancel this so you can see it. But it's not saying that yi theta becomes n y bar theta, etc. Like it's not corresponding. But if you work it out, you realize this is going to be 0. Okay, so that tells you that the sum pretty much in the exponent, it becomes the sum of these two. Okay, this carries information from the data set. Okay, and especially like deviations. This is the sum of square, right? We define this to be capital SS. Okay, but this is, I mean, even in the frequentist method, this is a commonly used measure over here. And down here, you can think of this as, so this is the sample mean, okay? This is the true mean that you believe it should be, okay? So this is trying to capture the information from there, okay? So I think algebraically, make sure that you know why this works, but also intuitively think about why you want to break it out in these two ways. And I realize, I mean, if you have taken like a linear regression like in econ department, I think there's some kind of derivations like this before or similar. I mean, this is pretty pretty standard if you try to understand how the normal model works. Okay. All right, so by the way, all of this part I think I actually left it in the slides. So I mean on the updated slides, so you can go back to check. But I think this one should be straightforward comparing to the next one that we're going to work with. Okay, so for now, assume that this is what we have. You just take it, and let's do the rest from here. Derive under the normal gamma prior distribution the posterior two distributions over here. So I would suggest you to try to, okay, let me clear this over here. I will suggest you to start with deriving. So first of all, you should try to write out what is the joint posterior, okay? I can write that for you, and then you can start from there. So this is collecting all of the terms from all of the priors, two priors, and then the data, the likelihood, okay? So this prior of theta, right? This is the contribution of the prior of the theta, right? And then let's write out the contribution of the prior of the phi, because it's a gamma, so we know that this is what you're gonna have, okay? So this is prior of phi, okay? Yeah, so the first one is a normal, and this one is a gamma. Okay, this is from the setup. And then let's combine what we derived earlier, because that's what contributes from the data, which is, so use SS0, and then exponent, two parts. Yeah, so this is what we have from before, okay? So all of this is from the likelihood. So this is Bayes' rule. And even, so in the last question of the midterm, it's pretty much using the same technique. But over there, there are more parameters. So I understand some of you are not sure like how they're related. But for this case, right now what we're dealing with, you have two parameters and then the likelihood. Okay, so the joint posterior, sorry about this. Yeah. So the joint posterior will be the joint prior times the likelihood. Okay, so I collected all the terms for you. So I will suggest you to go find this one first. Okay. And you know the results, I wrote it up in the handout. So try to figure out what that is. And then from there, we can figure out what's the condition of heat.
Yeah, and
yeah, so I think some of you tried it before class and it out, which is good. So again, in class, I don't think I will put it in like detail step by step, but there are some highlights I want to make and leave this as a homework question later. Yeah, so in order to come up, just a quick note, in order to come up the posterior theta given phi and y1 to yn, you need to collect all of the terms about theta, right, from the joint, okay? So if you do that, you will see that, okay, this is about theta, that's fine, the prior is fine, prior for phi is fine, and then here, nothing about theta, but theta is here, right? So that means you need this exponent, and then this exponent, right? So this is this, and this is that, okay? Yeah, because you only need the terms about theta. So I just want to draw your attention because there's some very subtle thing here that it's very easy to make mistake. So you notice that, like I put a phi to the power of 1 over 2 over here, okay? And that's very important because later you need this particular piece to recognize this to be a normal, okay? So once you do this, so look at the steps. You do the first step to get the phi, right? And then if you recognize that to be some kind of normal, which I will leave you as an exercise, that's really just algebra, but it's tedious, but you can do it. But then once you recognize the kernel of that, you need to make sure that you don't keep this again in the posterior for phi itself, because you already used that 1/2 copy in the posterior of theta. So once you move down here, you should have one less copy of this. So let me just, give me a second. Let me just explain this one more time. So I'm saying that like here, you should keep this phi to the power of 1/2 because you see, you know, like you were told that later you're gonna realize that this is gonna be a normal, right? So in order to complete the kernel for the normal, you have this phi to the power of 1/2 over there, right? But that means later when you're trying to derive the posterior for phi, you shouldn't have one extra this copy over here. So let me explain. So here you have to the half, right? And then here you have to the power of mu 0 over 2 minus 1. Here you have the power of n over 2, right? So naturally what you're gonna do, which is a common mistake that people make, will be okay. Because now I'm just trying to come up with the posterior for phi. I'm just collect all of the terms with phi, right? So that means I should have 1/2 from here. I should have no 0 over 2 minus 1 from here. And then n over 2 over here, right? In order to do like all of the powers for this. But then of course, all of the exponent that you're gonna do later, but that's something later. But I want to draw your attention because I think this is a common mistake, that if you do this, you realize you won't get the gamma that you're supposed to get in the handout that I gave to you. Because if you look at the handout in the end, the first parameter for the gamma is Vn, not n, mu n over 2, which is just mu 0 plus n, right? But then in order to have that, you shouldn't have this 1/2. So where did this 1/2 go? That's my point. So I want to draw your attention to this. So think about the steps. You have 2 steps. The first step is you come up, you try to derive the posterior for theta, which is a normal, right? In order to write out the entire posterior for this normal, you need to have a phi to the power of 1/2 over here. So you use that here already. You shouldn't keep it again when you're trying to derive the posterior for for phi itself. So that's why you shouldn't carry on this 1 over half, or like 1 over 2, because you used it over here. You needed to complete your posterior for theta, and then you used it there, so you shouldn't keep it. So in the power for phi, you should only have the rest, because this one needs to be there to come up to complete this posterior. So let me bring back maybe what we did, or even just in the midterm questions, or like all of the other exercises we had done before, especially all of the other exercises, because back then there's nothing conditioned, like nothing, no one parameter condition on another one. So you would never have seen a problem like a situation like this. But now, because theta is given phi, so if you come up with something for theta which used some copies of phi, you cannot carry it over. And then in the second step, you shouldn't keep it because you used it before. So I think a good way to think about all of this is think about the joint. Because eventually what you're trying to get, eventually I want to get the joint of phi theta given y1 and yn, right? And I write it to be theta given phi y1 to yn, right? Times phi given y1 to yn, right? This is the goal. Like we break it into two parts. We start with the prior and then we end with the posterior in this way. So let me just explain it again. This is what we want, and we know what it is. It's all this big monster up here. We just don't know how to deal with it, right? So I was suggesting you go with step 1, which is looking at the conditional, which is this step, the conditional of theta given phi and y1 to yn, right? So if you realize that this is a normal, and in order to realize this is a normal, you use a copy of this phi to the power of 1 over 2, you shouldn't keep that to the second part, because otherwise you have 1 extra phi to the power of 1/2. So if you think in this way, maybe it makes more sense. But overall, I think you need to convince yourself one way or another that you cannot carry this particular half over here to this one. So that's why some of you, maybe not right now, but in the past, some people were really trying to figure out what does 1/2 over there mean. You shouldn't be there because you used it already. Yes, Eli.
So I guess 2 quick questions.
Mm-hmm.
First is that phi of 1/2 is a constant, right?
It's a constant in terms of this. Yes. Yeah.
So more, I guess I'm not exactly understanding why would it not be more efficient to just pull it out like we do in all the other.
Right. Good point. Yeah. So good point. So I'm just saying that, okay, you can put it out. You can not even write it over here, right? But so then you were just, because you're a given phi, right? So that's your point. You're a given phi, so it's a constant. So I just need to work in the exponent and then realize what's the mean and variance, right? So I agree. Yeah, I agree. Except if you think about it, because now you're trying to get the joint, and you know what the joint is. It's whatever all of the terms up here, right? So I'm saying that in order to come up with the normal for this one, you need to have, it is constant, I agree. But in the joint, you use this phi to the 1/2. Because in the joint, in order to come up with this to be the normal, you have to use this. Yeah, it is a constant in term for theta, I agree. But because in the joint, you only have, say, 1/2 plus v naught over 2 minus 1 plus n over 2. This is all of the powers of phi that you have. Okay, you need to use this one for this normal. So when you're trying to derive the posterior for phi, you only need to care about the rest. You cannot double count it. That's what I mean. It is a constant for theta, but once you complete the normal kernel for it, you used a phi to the power of 1/2, and then you cannot reuse it again. So that's why I'm saying that some people will have 1 extra 1/2 over here that's not matching up with the result. And I think that's it's a really subtle point over here. But again, it's the same thing that you're trying to get the joint, and then the joint only have that many copies of power of phi. And then if you use it before, you shouldn't leave it there, even though it's a constant. What about another question?
Well, that other question is sort of a follow-up of this, which is that we've sort of defined the joint in two ways here. And I understand why in the second way we would be double counting. But in that first way, if you're just multiplying the likelihood with the two priors, as far as I can tell, there's no double counting there.
Oh yeah, there's no double counting. So that's why I'm saying that it's 1/2 here, right? And then this V0 over 2 minus 1. This is an over 2. There's no double counting. Yeah, that's all the terms over here.
So if you if you collect all the terms and feed an exponent there,
yeah,
just from that original way
right.
we create the joint,
right.
Looks to me like you still get 1/2 plus V naught over.
Good point. So okay, so this is kind of related to say, okay, now I don't get it through this step. So this two-step is you get theta given phi and then all of the data, and then phi given all of the data, right? What you're saying is, okay, I don't want to get phi, I don't want to get theta first. I want to get this first. And then that's all of the constants over there.
Or just what I'm saying is even if you just multiply it out on top, I mean it is an expression.
Mm-hmm.
We could just multiply out and we would have a phi of 1/2 plus V naught.
Yeah, so that's what I'm saying. So if you keep that, and then that will be expressing this particular term, that I consider everything else as constant or as given, and then I'm only looking at phi. So what I'm saying is, if you are doing from this step, like this procedure, you will need to complete the normal curve for the theta first.
Okay.
Yeah, and if you do that, then you're gonna use theta to the power of 1/2 over there, and because you used it, you cannot have it again. That's what I mean. Yeah. So I was saying that, okay, yeah, if you do this, what you described is this, and then that 1/2 will be there. But it's going to be a different distribution, as you can see. Yeah. So I'm just saying that for now, for this particular setup, we start with prior in this way, and then we go to posterior in this way as well. Yeah. Make sense? Mm-hmm. Okay. Okay, so right, I think for the likelihood part, I mean, most of the material is in the slide, so you can go back to look at it. For this particular posterior derivation, this is one part that I want to highlight, and the rest is tedious algebra. Okay, and yeah, I think it's still useful for us to make sure that we all know how to do it. So I will make it as a homework question, but in the meantime, if you have any doubts, I would really suggest you to go back, just sit down and try to do it, because obviously some of you tried it and it works. So it's not something that is beyond your reach, but this is a common mistake that I think might happen. So I want to make sure that you know what it is, okay? Alrighty, so let's continue from, yeah, we just have 10 minutes left, but I think I can cover the examples really quick, and then we know the background. Okay. So most of the slides, the rest of the slides is showing you the results, but a few things I want to talk about is the first of all is the gamma and inverse gamma. Okay, so because we're working with this phi right now, which is a gamma, and it's in the same way that 1 over sigma squared going to be a gamma, and then sigma itself is an inverse gamma distribution. Okay. We won't go into detail about this inverse gamma, because if you work with precision everywhere, you'll be fine. Everything will just be gamma, and then we know this before. Okay? So this is the first highlight, and then second is, yeah, so this is the results that you were supposed to derive, and for now we will take it as what it is, and I want to show you the analysis using this particular non-informative prior here, which is, let's have the prior just to be 1 over phi. Okay, and this one, again, it's just by tradition, and we call it non-informative prior because it's only, so the joint of the prior is only 1 over phi. And then let's take it for now, And then you will see that the result is going to simplify to this two. Okay, so the mean, the posterior mean, going to sample at the mean of the data, and then the variance will be 1 over n times phi. Okay, and the phi, the posterior in the gamma is n over 2 and ss over 2. And this will be the one that I use for demonstrating the results. But later, once I finish that, we can come back to see what does this mean, why we're doing this non-informative prior over here. Okay, but for now, I want to know that this is what we're using. So if you actually do it in the particular question that I talked about, say you want to answer some of the questions like this: is the average improvement for the accelerate group larger than that for the no growth group? Then you're trying to get this probability, right? In posterior, you try to get the mean A, mu A larger than mu N given the data. Or if you want to look at the variance of the improvement, then you can do this. And then what if I want to do something like we did it before, the ratio of the mean and the standard deviation, then we can do that for two groups and then compare. And lastly, of course, if you want to make predictions, if you want to say that now I have a bunch of new kids and I will randomly put them into these two separate groups, how much change they're going to have, right? So that will be a prediction problem. Then you'll be able to answer it by using the posterior predictive distributions for both of these two. Okay, so suppose this will be some of the questions that you want to do. Then you notice that, again, we don't need R at all to do all of this except for the posterior predictive, because everything before that is analytically resolved, right? You know the exact normal and the gamma distribution that you have. So you see that. So this is the data that we have, okay? And I also give you the sum of squares for group A and sum of squares for group, oh, I should use N over here, sorry about that. So then pretty much the posterior distribution, because we derived it before, will just be mu is a normal, and then phi is a gamma as well for the A group and the N group. Okay, and then you know what the values are because that's based on the data that you have. So once you can derive all of this directly, you'll be able to make inference about all of this. So I say, like, if you want to do predictives, if you want to put some priors here and there, I included some examples and then some ways of doing it over there. And I think it's probably easier if you go back to read it more carefully later. But overall, I want to show you that because for the two parameter model case, two parameter normal model, we can derive this two. So whatever the data carries the information, you'll be able to answer some of the questions that I posted earlier. Okay? But once, if you want to do predictives, then you will need to use R or some other software to do multi-color approximation. Okay? So in a rush, because I want to bring back one thing that we talked about, we didn't get the chance to talk about, because this is, again, interpretation of what the posterior means to us is always important. So I want to take the last 5 minutes to talk about this. So here we have two priors, okay? And two posteriors then. So the top two is about phi, is about theta, sorry. And the second set of two over here is about phi, okay? So you notice that the posterior, look at the handout, the results are there, so maybe easier to read because I couldn't fit everything in the same slide. So kappa 0, remember, we're talking about as the prior sample size. So now, based on the derivation that you will see that you can do, you'll notice that we have this kappa n to be kappa 0 plus sample size. Okay? So all of this works in terms of sample size. Okay? So kappa 0 is prior sample size, n is data size, which is the sample size itself. So they sum up to be the total weights in some sense. Okay? And that's what you see. Again, the posterior mean of the normal is a weighted average of the prior mean and the sample mean. Okay, so nothing surprising. But now we're also working with phi. remember? So this phi is a gamma. So how can we understand the impact of the prior and the data on this gamma distribution? So let me tell you, in the prior, it is V null over 2, and then SS null over 2. Now in the posterior, it becomes, let me write it for you. It is gamma, so we use Vn over 2, and let me see what I use, SSN over 2. But of course, Vn is V null plus n, and then SSN is sum of 3 terms. So let me actually just put it over here. So let's pause here a little bit to think about, because this is new. The gamma interpretation is something we never did before. So I want to take the moment to think about it. But the previous ones about the mean, which is a normal, is what we have done before. I think there's an analogy over there. So what about this Vn and SSN? So Vn is the sum of V null and n. Okay, so again, if you can try to convince yourself that this again is some kind of prior size here. Okay, you have the prior size to be V null, and then data size, and then you come up with a final size, which is the final weight. Okay, and then of course this SSN is a little bit complicated to understand. So this earlier, this is from the prior, right? And this is from the data, the sum of squares. And this is some extra terms that is just left there in terms of when you're trying to do the derivations. Okay, there are some extra terms over there. So this SSN can be considered as the total posterior variation. And notice the parts of this. So if you understand this to be the total posterior variation, you see that you have the contribution from the prior variation, right? Which is SS0. You also have the contribution from the data variation, which is the sum of square from the data, which is SS. And then you have something extra, which if you read it carefully, is Y bar minus mu 0. Y bar is the sample mean. And mu 0 is the prior mean. Right? Yeah. So this, you can think about it as the variation between the prior mean and the sample mean, but then multiply with certain constants, so weighted in some way. Okay, so hopefully you will see that, or you can try to see that. This is why we start to use SS0, SSN, and then break things down in this way. Because in the end, we're trying to still make sense of the algebra that we have done. I mean, the algebra itself is tedious, I agree, and may not be very enjoyable to do. But once you have done it, I think you'll feel a little bit accomplished. And then in the end, hopefully you'll be able to see why this is the case, and then how this parameterization makes sense to most of people. Okay? All right, cool. So I think this will be the end of the normal model. And then when we come back next week, the week after, because we're going to have October break, the week after we're going to start doing give sampler. Okay, and again, you can do corrections. So after class today, I will send emails is where you can sign up for the midterm corrections if you want to do, and you're going to get 50% back if you want. And I will also post homework 5, because homework 4 is on normal model. You can start doing it already, but it won't be due until, like, it won't be due like that Monday when we come back. It's probably that Wednesday. So you will take some time to do it. Okay? Oh yeah, let me just close this. Okay. Yeah.